Okay, I guess let's get started. So in this lecture, what we're going to do is that at the beginning, we're going to talk about deep learning, especially some of the challenges in deep learning theory. And then in the next probably like 5 to 10 lectures, we are going to discuss different aspects about deep learning. I guess you'll see like we're going to talk about optimization, generalization, so on and so forth. So basically in deep learning theory, there are kind of like different aspects. For example, optimization, which we'll spend probably 2 lectures on later. And generalization is another question which we probably will talk about for probably more than 3 lectures. And at the end of the course, we're going to talk about some other slightly different topics. So in some sense, you can view this as a kind of like an outline for the next 5 weeks. So to talk about deep learning theory, I think it's probably useful to somewhat kind of like summarize the classical machine learning theory, which I actually didn't really talk about that much as you know, from a bird's eye view that much in the beginning of the course, because I felt that if you give too much information at the beginning, it's probably a little bit too much. So, but now I'm going to kind of have a kind of like higher level view about what classical machine learning theory do in terms of different kind of like aspects or different kind of like topics. So I guess in the more classical machine learning theory, there are several things. So one thing is called approximation theory. So so in some sense, this another keyword is called expressivity or representational power. If you see these kind of things, you know that representational power. So you know that they are all about the same thing. So what they are doing is really caring about, basically you want to bound L theta star, which is the best model in your family. So far, until this week, we always talk about excess risk. We compare it with the best model in the class, and we said that if you can get the best model in the class, then you are done, right? But actually, it's not done, because maybe you are using the wrong hypothesis class. So your best hypothesis class in the family hypothesis class, the best hypothesis in the hypothesis class is probably not great, right? So approximation theory is basically trying to deal with this, right? You are trying to understand whether your hypothesis class is powerful enough to express the functions you care about. So, for example, in a kind of trivial case, for example, suppose you have some data like this, and right, something like this, some positive data, some negative data. Here, you know that if you use linear model, then the best model, linear model, is not going to do great, right? Because if you probably find the best linear model, you probably would do something like this, I don't know. So in this case, you can say that L theta star wouldn't be great if you choose your capital theta to be linear family, and then you can study what hypothesis class can contain a good classifier, even you have access to population data, so on and so forth, right? So in some sense, this is trying to understand how good can my hypothesis class H approximate the ground truth label function, right? So that's one type of question. So and another type of question is what we discussed already, so which is about the statistical aspect of, sometimes people call it generalization theory. So this is about the excess risk, as we discussed in the last several weeks. So you are trying to bound from above the difference between your learned hypothesis from the best hypothesis theta star, right? So and what we have done was something like you bound this by L theta hat minus L height theta hat plus L theta star minus L height theta star, right? So, and people have called this the generalization error. Right, the generalization error is the difference between the population loss and empirical loss on the learned parameter. Right, so this is the generalization loss. Basically, the difference between training loss and test loss, right? On the learned parameter, theta hat. If theta hat is ERM, then this is talking about ERM, but maybe in other cases you are using some other algorithm to find theta hat, then you bound the generalization error for that theta hat. And this term, as we argued, the second term is always small. Just no matter what hypothesis class you use, basically as long as your loss function is bounded, then this term is always something like 1 over square root n. So basically that's why we don't care about this term that much. Okay, so and what we have done was something like you prove this kind of generalization bound of the, so you prove something like L theta hat minus L hat theta hat be bounded by something like some complexity over square root n. I guess typically probably you should write this. Right, so and this, the principle here is that if your hypothesis class is of low complexity, then you have better generalization error. Right, so simple hypotheses all like can generalize better. So I think this sometimes also people call this outcomes razor. This is, I think, is kind of like philosophical principle which dates back to something like 1100 or like some around that time. And the principle is something like simple or parsimonious explanation can generalize better to other situations. And you can see even from these two things, right, you can see that there's some kind of like a conflict or trade-off between the approximation theory and the generalization theory. Because if you use a very, very simple hypothesis class, then your L theta star may not be good enough. Right? For example, for the data I drew here, if you use linear model, then your L theta star is not great, but your generalization error could be very good because your model is linear and simple. So there's some trade-off between, and I think people also sometimes call this bias and variance, right? So the variance mostly corresponds to generalization theory. It corresponds to statistical error introduced from learning because you have finite data. That's why you have to pay something that depends on how many examples you have. That's the kind of the variance. And the bias mostly is a quantity that only depends, bias or the expressivity is a quantity that depends on the fundamental power of your hypothesis class. It's not something that depends on how many examples you have, right? So, but the bias variance trade-off thing, right, is essentially the same thing here, but the exact definition of bias and variance can only apply to basically square laws and linear model. That's why we don't use them explicitly here, but the principles are somewhat related. So, and you can also kind of like extend this generalization theory a little bit by saying that you can have you can consider the regularized loss. This is, in some sense, you can consider this as a application or implication of the generalization theory, which says that if you use regularized loss, right, something like L hat reg is something like L hat theta plus lambda r theta, where this is a regularizer that captures the complexity of the hypothesis. So then you can hope to have claim like this. So you can have a statistical claim of the following form. Of course, this depends on exactly what regularizer you use, what model, so on and so forth. But the form of the claim is something like if theta lambda hat is the global minimizer of L hat reg, then you have a generalization bound. You can bound the excess risk, or you can bound either, I guess, either the excess risk or the generalization error. I guess they are pretty much related, as we have discussed, right? So all the generalization error, right? So they are bounded by something. So this is the type of results you probably get from this kind of statistical, the generalization theory, because you know that the reason is that if you optimize this regularized loss, and you indeed find a very small regularized loss, that means that your regularizer, the R theta, the complexity, right, is small, and also it means that your training error is small. And then if both of these are small, then you can show that your excess risk is small, right? Because this model will generalize to the population or the test case. So and then there's a third aspect, which is called optimization. Any questions so far? Right. So there's a third aspect, which is called optimization. So the question is about how to numerically find theta hat. Right. Theta hat could be the argmean of the training loss, or maybe you can talk about theta hat lambda, the regularized loss, something like this. Right. So and this is a purely, at least in the classical way of thinking about this, you can basically view this as a separate question about, you can forget about where your data come from. You can forget about, why you care about minimizing this training loss. You just say that I'm giving this training loss, that's my job, right? So, and typically the approach is something like, you can, if the loss function is convex, you use convex optimization. And or maybe you can use gradient descent for non-convex functions, so on and so forth. Or maybe stochastic gradient descent. There are many different approaches. And when you measure the success, or you measure the interface, is that you care about how well you can approximate the minimizer. You can never find the exact minimizer, right, using a numerical approach, right? So you always have some small error compared to the minimizer of the empirical loss, and you can measure the error in different ways. Maybe measure the error in terms of the suboptimality, in terms of how different your minimizer is in terms of the loss function compared to the best minimizer, or you can compare other kind of quantities. So in some sense, I think from this kind of like the summary here, you can think of the statistical part is kind of pretty much independent from the optimization part. Of course, there are also interesting interface. For example, you can also ask about what regularizer. So when you write regularizer, right? So you can ask the question, what regularizer can simultaneously have good statistical performance, but also can be easy to optimize, right? So, and by easy to optimize, it means that you can optimize it fast, or maybe optimize it in a certain time, maybe d time or d squared time, so on and so forth. So there are still interactions between different parts, but if you just need a kind of like high level kind of understanding, you can think of them as kind of separate parts, right? The interaction are more on the lower level details about how do you achieve the best statistical efficiency, or how do you achieve the best computational and statistical efficiency. Then you have to talk about the interactions. But at a high level, you don't have to think about them simultaneously. You can think of them roughly separately. That's the question.
Can you give some indication as to why that ratio should be bounded by something?
Sorry. Oh, no. This is not a ratio. Sorry, my bad. This is just two things. My bad. My writing is bad. And these two quantities are basically similar, right? So like you care about the excess risk, which is the most important thing, but which is almost the same as the generalization error, right? So and actually you bound the generalization error, then you bound excess risk. Sorry, my writing is not quite clear. Okay, so any questions so far? So these are the standard way of thinking about these questions. But what happens in deep learning? What happens in deep learning is that, as you see, things becomes more complicated, and for a fundamental reason. And I think the first thing is that for deep learning, there are probably two things that changed, at least on the surface. So one thing that changes is that you have, from linear model, it becomes nonlinear model, right? So, and this directly affects the optimization, because when you have nonlinear model, it becomes non-convex loss, right? But this wouldn't, change things, wouldn't change the structure, right? Like the structure view fundamentally, because it just makes the optimization question harder, right? So at least at the beginning, this is what I thought, 5 years ago, maybe like more than 5 years ago, when I was started to do deep learning theory, right after deep learning took off, right? I thought at very first, I thought that the only difference is that now your optimization question becomes harder. So and then the question is just how do you optimize better? But then I think in probably like about 3 or 4 years ago, people realized that there's also another fundamental difference from the statistical perspective, which is that empirically you always use this so-called over-parameterized model. Okay, maybe it's not precisely to say that you always use over-parameterized model, but generally over-parameterized models are better than like more parameters are always generally better, almost always better. So more parameters generally helps. And it can help even to the extent that when your parameters are more than the number of data points, right? So it even helps when D is larger than N, this still helps. And it even helps when you have already zero training error. So even after you already have zero training error. So this is a plot that I got from some paper. This is from a paper by Nishaba, Tomika, and Shabro in 2015. So this is what they've found. Of course, this is only a very small data set, but roughly speaking, the same phenomenon also holds for larger data set. And you can see here that the black curve is the training error, and the x-axis is how many hidden units or how large the network is. Hidden units means the number of neurons in your network, which if you have more hidden neurons, you have more parameters. And actually, it's quadratic in the number of hidden, like the number of parameters is quadratic in the hidden neurons in this fully connected case. This is a very simple fully connected network on MNIST. And you can see that after you have more than 64 hidden neurons, you can fit MNIST perfectly. Like 0% error. I think literally zero, maybe not exactly literally, maybe 0.101% error, something like that. And if you look at a typical textbook, right? So what you would do is that you would predict that the test error will go up after a certain point because you are overfitting. You are using too complex of a model and you are overfitting to the data. Right? That's the purple thing, which you would probably read from some of the classical textbooks. And actually, it does happen in some classical settings, but just not happen often in neural networks, or probably never happens in neural networks. And what really happens is the right one. The generalization error actually continue to improve as you have more and more neurons, even though you already even memorize everything, right? So if you compare 64 versus 4K, basically these are just two neurons. Oh, sorry, these are just two neural networks. Both of them fit the training data with 100% accuracy, but one of them has better test accuracy than the other. So this is the kind of a big mystery from a theoretical point of view, especially if you believe in the classical trade-off between bias and variance, or the trade-off between expressivity and generalization theory, generalization power. So this is the big open question, right? So and let me briefly discuss, again, what's the impact on each of these concepts, right? And actually, you even have to rethink about some of these concepts, like how to some of these concepts becomes entangled or intertwined now in deep learning. So first of all, for approximation theory, I think we don't really change, things don't change that much, at least compared to other parts. So for approximation theory, I think generally, I guess, you know that, large models are expressive. And there's actually something called universal approximation theorem. I'm not sure if you heard of it not. In some sense, this is saying that if you have a network that is wide enough, then you can approximate any functions. Of course, that's in some sense a misleading way to say it, because what does it mean by large enough, right? So if you need exponential number of neurons, that's indeed very large. That's large enough, but that's not really implementable, right? So empirically, you don't even need that many neurons to be expressive. I think you just need polynomial number of neurons. But anyway, so the gist is that we do believe, regardless of whether this universal approximation theory is exactly answering the question, at least we believe that the neural networks are very powerful. So we generally believe that the best model in this family, especially if you use a wide enough network, this is generally small. This is what we generally believe, and at least what you can show is that, you can say this is really small. The minimizer of the training loss, because if you have a neural network with more than n neurons, so this is just because with more than n neurons, n is the number of examples, you can proofly memorize all the training examples. At least you can find one network that memorizes all the training examples. That network may not generalize, but this already means that your minimum training loss is very small. It's probably 0. Okay, so basically for approximation theory, I think we generally believe that the models are very expressive. And then that becomes the generalization part, which becomes quite complicated. So there's another kind of like a information about what practical network does, is that in practice, also people don't use very strong regularization. Only weak regularizations are used. And this is kind of like a somewhat important thing to say, just because recall that even in a classical setting, right? It's not always that you can show like sometimes you can have even in a classical setting, you can have the setting there where you have a lot of parameters, but you have a strong regularization to compensate. So that's allowed in a classical setting, right? For example, if you have use a sparse linear regression where you have a lot of features, the dimensionality is very high, but you regularize the sparsity of your linear model, then wait, I think, speaking of sparse linear model, I think I forgot to do something that we are left last time about the comparison between linear models. But okay, anyway, my bad. I think I should have that. But anyway, let's continue with this. But anyway, so what I was saying is that even in the classical case, you do allow to have very big, you do allow to have d bigger than n, right? The dimension can be bigger than n as long as you use a regularization, right? Because if you use a regularization, you implicitly restrict the complexity. For example, if you say that the sparsity of your model is S and S is less than N, then that's okay. So, however, in deep learning, in practice, we only use very weak regularization, right? So typically just some L2. At least even with L2 you can work. Sometimes even without L2 you can work pretty well. And also the regularization strength is also relatively small. The strength is small enough so that you can still fit your training data basically 100% with basically 100% accuracy. So and another way to say the weakness of the regularization is that you can consider the following fact. So this regularized loss, right? If you just regularize with for example, you just regularize with something like L2 with some lambda, the regularized loss doesn't have unique global minimizer. So, or at least it has very different approximate global minimizer, right? Maybe if you really care about the numerical precision, right? If you say like you care about the like 10, like you care about very small, accuracy, precision, then maybe there's a unique global minimizer. But for practical, purposes, there are many different global minimizers that are very similar in terms of the training accuracy and all in terms of the regularized loss. So, and they all have very small regularized loss. They have very small loss from the regularizer part. They also have very small loss from the training error part. And there are different global minimizers. And it's also, and another thing is that it's also not true that all of these global minimizers perform the same. So these global minimizers perform the same. On the test. I guess probably it's easier to just have a figure here. I think I did prepare a figure. So, so let's see. I think this is experiment I've done a few years back. There are many different kind of like plots you can find online on different papers like this. This is just one of them. I actually took a little bit to exacerbate the differences a little bit, but the gist is the same. So this is what? This is CFAR10, and you have two algorithms, the red one or the blue one. And I'm plotting the training and the test. And these two algorithms only differ by the learning rate. They have the same training objective. They have the same regularization strength. It's just that the optimizer are different. So at the end of the day, you see that both of these two algorithms found some global minimizer or approximate global minimizer. You can see the training error is close to 0 in both of the two cases, right? And so both of these are global mean in some sense, or at least approximate global mean up to very good approximation. But you can see that their test error are very different. So that means that these are two different global mean for sure, right, in the parameter space. And also they perform very differently on a test. So, so that's the kind of the mystery, right? Because this kind of refutes the possibility to have a theorem like in the classical case, right? So recall that in the classical case, typically you have theorem like this, where I'm saying, yeah. So you have theorems like this, right? So saying something like, if you find the global minimizer or a global minimizer or any global minimizer of the regularized loss, then you can generalize. You can bound the generalization error. And this is no longer the case because not all the global minimizers are the same, right? Some of them are better, some of them are worse, and you probably shouldn't have the same bound for all of them. And some of them probably just don't generalize at all, right? So this is saying that you cannot just say any global minimizer generalized. You have to somehow distinguish different global minimizers found by different algorithms. So this basically means that but what happens here, right? So what happens is that the optimization starts coming into play, and this is the reason. So basically, as I alluded to in some sense, like different optimizers found different global minima, and some of them are better, and some of them are worse. So that is saying that optimization is not only about finding any minimizers, any global mean. If you just say you find a global mean, that's not enough. You have to use optimization to find the right global mean. So in some sense, the optimization have two jobs. One thing is that you have to find something that has smaller error or a small error or small regularized loss. And the other job is that it also has to find something that generalizes. Right? It has to find a global minimum that can generalize. So in some sense, the kind of the picture is like this in my mind. So you have this I'm using one-dimensional thing, right? This is the parameter, this dimension is the parameter. And basically, I'm envisioning this kind of toy case where you have the landscape of the training loss and test loss look like this, right? So the training loss has two global minimum. And one of them is a good global minimum, and the other one is a bad one. And the bad one in the sense that the corresponding test error is bad. And the optimization algorithm is not only responsible for finding an arbitrary global mean, it's also it actually has to find the right global mean instead of the bad global mean. So somehow the optimization algorithm is doing something beyond what it's supposed to do, right? So I guess in some sense, this is a one-dimensional case. If you think about the high-dimensional case, this is something I often use in my slides. It's kind of like you are going to a ski resort, and the first time I came to America, I didn't realize that you can have multiple valleys or multiple parking lots in the same ski resort. So when I go back home, right, I just I do follow gradient descent, right? I just go to an arbitrary kind of like a valley, and I found that my car was not there, and then it's actually a trouble because the resort is closed and you cannot lift you up, and so it's actually pretty annoying. But then I realized that actually there are multiple global minimum, and one of them is better than the others. So and you have to find it. So it's not like arbitrary gradient descent. Or maybe the gradient descent is doing something more than just the arbitrary downhill skiing. Right?
So just to understand this, like what part of generalization to these classes breaks down? Like, is it the fact that the bound becomes vacuous?
Right. So why the generalization? So the question is exactly mathematically where the generalization theory breaks down. I think the bounds becomes vacuous. Basically the bounds you can prove becomes vacuous. The bound you can prove under this language, under the existing language, becomes vacuous. So basically, if you say that you want to prove a bound that works for all neural network of size 10 million or of size like 100 million, right, for only 1 million examples, right? So if that's the language you are using, then it wouldn't work anymore. So you have to have a more precise way to think about it. Does that answer the question to some extent?
Yeah, so but then, like, what if you use a different comparison? Like, what if you incorporate the fact that like this neural network has 10 million parameters, but because of the constraints imposed by FPGA, like expressivity is not exactly that.
Right. That's roughly speaking, that's the approach we're going to take. But there's a one problem with this. If you just do exactly what you said, there's a problem which is you're going to get the same bound for any algorithm, right? But empirically, different algorithms have different performance. And the way to fix it is becomes that you first say that different algorithm find models with different complexity, and then you can have different bounds for them. So the algorithm has to come into play in some way, right? So yeah, so basically that's the kind of the conclusion here. So the algorithm has to come into play in your statistical analysis, right? Because if you don't have the algorithm there, you are not going to distinguish these different algorithms, right? So in some sense, you entangle the statistics with optimization to some extent. And now so basically the way to fix it is at least the kind of the current plan, the general kind of agenda. I think most of the researchers agree on, seems to agree on, is that you analyze the optimization and analyze why the optimizer find a good local minimum. So basically, you want optimizer. You need to have a theory that says something like the optimizer find a theta hat such that the theta hat is a global mean that's probably or approximate global mean of the empirical risk, and also 2, theta hat has some special property that you didn't explicitly say that they should do, right? For example, the property could be low complexity. So maybe, for example, just to give you an extreme case, for example, you run an algorithm without any regularization, but then magically you say that even though I didn't let it to regularize, but actually the theta hat I found has low L2 norm, or has even the minimum L2 norm. Actually, you can prove these kind of theorems in certain cases. So, and then because of this special property thing, and this implies that it can generalize. Right. So, and people have kind of like proved theorems of this kind of form in many different cases. For example, wait. Sorry. Right. So for example, you can talk about SGD, right? So SGD probably has some special preferences in terms of what models they want to find. And maybe SGD with different kind of like specifications, right? So you can have large and rate, small batch and so forth. I'll talk about that in a moment. But generally, we want to say that the optimizer, the practical optimizer people are using, can have some preferences on certain type of global minimizer. So, and then after you have this, right, like as I said, after you have the special preference, then you can use so this part, right, from the special property, the low complexity, to generalization, this could be kind of more classical. This could be classical theory, right? Or maybe improvement of classical theory, depending on what complex measure you are talking about, right? As you suggested. So, so that's kind of the kind of like the current kind of like status quo of explaining deep learning theory. Of course, there are other kind of like approaches, but I think this is pretty much, I think, kind of like the high level. People have almost reached a consensus on the high level approach here, I think. And what are the kind of the best results? Let me have a brief summary of what are the best results people know, roughly speaking, in each of these aspects. So basically, first of all, for I guess, sorry. So let me just make this a little more formal. So I guess, a little more formally. So basically, you have probably 3 tasks, in my language. So first, you prove that, I guess, I'm repeating myself a little bit in some sense, So you prove that the optimizer converges to approximate local global mean of L hat theta. And then in the second task, you also have to prove that in addition to 1, the theta hat also has low complexity. For example, something like R theta hat is less than C for some complexity measure. R. And this R depends on the algorithm, depends on even the details in the algorithm, like learning rate, batch size, so on and so forth. And then task 3, you say that for every theta, such that R theta is less than C, and maybe L hat theta is close to 0. So for every theta with low complexity and small training error, we have the test error. L theta is also small. So that's kind of like the general idea. And what we have done, what people have done in this kind of area. So I guess so regarding the task 1, right, which is the optimization question, right? Task 1 is optimization. So I think maybe if you want to associate some keyword to this, people would call this the first question optimization, and the second question people often call this implicit regularization effect. Yeah, probably I should explain this because this is implicit because you never told the algorithm to minimize this complexity, right? It's implicit in the optimization procedure, and it's a regularization effect because you get some low complexity solution. And the third one, this is probably like the more or less the classical generalization bound, right? And for task one, I think what happens is that if you don't have regularization, so I guess, sorry. So for task one, I think for the optimization question, so one of research, consider the case where you don't have overparameterization. This is overparameterization. Without overparameterization, in some special case, you can still prove this in some special case. For example, matrix factorization problem. Maybe linearized network. Or maybe something like tensor decomposition. You can show that gradient descent or SGD can converge to global mean. So here, linearized network means that you don't have any activations. Basically, your activation is linear, so you just stack a bunch of linear models, which doesn't really do anything from a statistical point of view. It's just purely you only analyze that as an exercise for your technique in some sense. But you can still publish papers in it just because everything about optimization is very complicated. Even analyzing linearized network is difficult. So this is the one thing that people have done. But you can see that this doesn't really address all the issues, right? Because you don't allow overparameterization, and it only works for linearized network, all matrix factorization problem like matrix completion, so on and so forth. So and recently, in the last 3 or 4 years, I think, so you can also do this optimization question for neural networks, for any neural networks, for almost any neural networks, deep, shallow, so on and so forth. But with the caveat that you have to, for special hyperparameters. So special hyperparameters means something like, maybe like so first of all, you need overparameterization. That's actually probably good because anyway, empirically people use overparameterization. But the limitation is that you also need special learning rate or an initialization, special initialization and learning rate, so on and so forth. So, and that becomes a problem. And by the way, this is typically called NTK approach, neural tangent kernel, which I'm going to talk more in the future lectures and explain why this is called neural tangent kernel. So this is the so-called NTK approach. And the problem with this approach is that this special initialization is a problem, and also special learning rate or special algorithm. So you also have something maybe. So this is also, you also need something about batch size. For example, in most of the paper, you have to the batch size to be very big. You can only analyze gradient descent. You cannot have like stochastic gradient descent. So this, this is kind of like the restriction on the hyperparameters. At the beginning, we thought, okay, that's not a big problem, right? We have these hyperparameters, and then next day we probably extend them to other hyperparameters. But it turns out that there is some serious limitation in the hyperparameters because, as I motivated before, even you change the learning rate schedule, right? In the figure we found, right? So this is a real experiment. Even you change the learning rate schedule, you change the performance of your model. So it's not, so if you analyze a special learning rate schedule and you analyze a special initialization, then maybe you are not actually analyzing anything impressive, right? So so for example, like in this NTK case, I think what we can analyze, the algorithm you can analyze wouldn't give you the best performance that deep learning offers. You probably get something like 80% on CFR, but the best algorithm probably get like 95%. Of course, there are improvements to along this line, but generally, the issue is that you make this hyperparameter so special so that you lose the correct implicit regularization effect of the optimizers. And you're analyzing an optimizer that doesn't have the correct implicit regularization effect, so that they don't generalize as well as the real deep learning algorithms. But still, I'm going to talk about this because this is a very nice idea, and in certain cases is pretty useful. So and then for the implicit regularization question, right? So the question about why the algorithm, why the optimizer prefers certain kind of like a low complexity model, people have had a lot of results on special cases. So special models, and actually maybe I should call it simplified models. My bad. I don't know why. Somebody took my yoga mat, yoga break for some reason, and I have to use the book. Anyway, so special or simplified models, and also special optimizers. But here the special is in a right way. So you're analyzing the effect of the optimizer. So you focus on each aspect, in each paper in some sense. So what are the models that people have analyzed? For example, linear regression. This is something you can say, and here you can say that certain initialization prefers certain kind of like models. And you can also talk about logistic regression, logistic linear regression. And here we will see that you can prove something like even the model just wants to find the minimum, like even the model just tries to minimize the logistic loss, actually tries to find the max margin solution. So, and also for matrix sensing or matrix factorization problems, and linear neural network. So you can talk about this, and also there are special aspects of the optimizers. Of course, this is sometimes there has to be a combination of the problem and the optimizer, because certain optimizers wouldn't have implicit regularization for certain problems. So you can talk about the GD, you can talk about SGD, and SGD. I think there's actually also about the noise covariance, like what covariance will give you the right implicit regularization. Also the noise scale, which also matters. And you can also talk about, for example, dropout. This is something you do in your optimizer, which will change the implicit bias. And you can also talk about learning rate, which is also actually important. And batch size, so on and so forth. And also there are unsolved open questions, for example, momentum, like batch normalization. All of this has some implicit regularization effect. So that's why this becomes complicated, right? So everything you do in your optimizer, everything you change, right, would possibly have an implicit regularization effect. Sometimes it's positive, sometimes it's negative. Of course, most of the tricks that we have seen have positive effect, because that's why they survive and they are published, right? So that's the statistical, I guess. And I'm also going to try to mention a more general result that we have, like me and some collaborators have done. So you can also try to have a more general result, which says something like, SGD on L hat theta is roughly equivalent to doing gradient descent on L hat theta plus some L lambda R theta for some R, for some regulator R. Right? This is a result that we can show. Like this is a much simplified, the high-level idea of a result that we can show. But of course, there are limitations, right? So this kind of more general result have weakness in other aspects. For example, you may have additional assumptions, or you can only deal with certain kind of stochasticity, so on and so forth. I think from this result, you can see that this is kind of the things that we are trying to do, right? So if you add stochasticity, then you automatically, implicitly, you got a regulator for free, even though you are using stochastic within descent on the original training loss, but somehow you get optimizer for free somewhere. Okay, so I think yeah, so basically we are going to talk about many of this in the next few lectures, in the future lectures. And for the task 3, for the generalization bound, this is also like an interesting open question for deep learning, because you also want to have precise generalization bounds that can be compatible with the regularizer you got from the previous part, right? So we have said that the optimizer has a preference, but does that preference lead to a better generalization? That's another open question, right? So for example, you can have one of the paper in 2017 proved that for this, if you use this as the complexity measure, where AI is the weights of ith layer. So if you use this, then you can guarantee a generalization bound. That's one of the early results along this line. But the problem with this is that this is not precise enough, right? This is still too big, too demanding in some sense, right? So you sometimes need more precise, optimizers. For example, if you can guarantee that, I guess I will talk about the limitations probably when I really talk about this, but this is still not precise enough. And you sometimes need more fine-grained, more fine-grained complexity measure that is more compatible, more fine-grained. And also ideally you want something that is a result of the optimizer, right? So you want this regularizer here to be the same regularizer as what you had in the implicit regularization effect part. So that's the third part. Yeah, I think that's basically a high-level overview of some of the lectures we're going to talk about. Some of the lectures in the next few weeks. And of course, there are other open questions in deep learning as well. For example, what's the role of the parameterization, right? So in these tasks, I didn't mention any of those, so on and so forth. But for those kind of things, I don't think there's a systematic study yet, so that's why we don't talk about them much for now. And I think for the intermediate plan, I'm going to talk about task 3 here first. Because we are in this mode of proving generalization bound, right? We have talked about Rademacher complexity. And all of this depends on the Rademacher complexity. And I'm going to talk about that first, and then I'm going to move on to the other parts. Any questions so far?
We haven't really looked at the data that might be coming from the spreadsheet.
Sorry, I didn't hear the question.
None of these tasks assume anything about the data. Like the data could be anything.
Yeah. I got the question. Yeah. So the question is whether any of these results or tasks, depends on the data distribution. Yes, they all depend on data distribution, I think. So all of them assume some data distribution underlying. So some of them will require something stronger. Some of them just require some regularity condition. But I don't think you can go away without any data distribution assumption. Yeah, and some of them have very strong data distribution assumption, to be fair. And that's actually, in some sense, one of the, in my opinion, that's one of the technical challenge here. Like it's kind of like a subtle balance. If you assume too much about the data, then you lose the realisticness. But if you assume something too strong, then but if you assume too less about data, then you have some hardness result. So certainly without any data assumption, you probably shouldn't be able to prove almost any results here, just because things becomes NP hard, especially if you talk about computational procedure. It's very easy to get into NP hard instance. So we need some data distribution assumption. And another kind of even more complex question is that, how do you leverage your data distribution assumption? Like we don't have a lot of tools. So for example, if you assume it's Gaussian, then what you know something about, what's the moment, so on and so forth, right? You can do some certain kind of derivations. But I don't feel like we use even the property for Gaussian enough in some sense, and let alone other kind of like data distribution assumption. We don't have a lot of good tools to use them. Cool. So if there's no any other questions, I'm going to move on to the generalization bound for neural networks. So, and you can see that this is still roughly in the kind of mindset of the classical setting. Even the only difference is that we are looking for proper complex measures, not only the dimension dependency, but something more, sometimes more complicated. Okay. And you will see that this part is really a direct extension of what we have done in the last 3 weeks, because the tools are shared, and it's really just that you need better tools in some sense. Okay, so all right, so now let's talk about the particular setup that we can do. So we're going to start with 2 layers, 2-layer neural networks, and then in the next few lectures we're going to move on to multiple layers. And for 2 layers, let's use the following notation. So let's say your parameter theta contains of 2 parts. One part is W and the other part is U. So W is the second layer, and U is the first layer. So basically your neural network F theta X will be something like W transpose phi of UX, where U is a matrix that maps dimension D to dimension M, where M is the number of neurons. So basically UX will be M dimensional. So this will be M dimensional, and you apply an element-wise ReLU function. So phi is element-wise ReLU function. So phi of a vector z1 up to zm is equals to basically you apply the entry-wise, you get max z1 0 to max zm 0. Right, so after you apply phi, you get m-dimensional vector, and then you inner product with W, you get a single scalar. So we have a model that outputs a single scalar using these 2 layers, U and W. And again, we still call xi, yi the training data set as usual. Okay, so our goal is that we first show a Rademacher complexity bound, and then we also talk about how this RC bound is relevant to practice. Okay, so and I think for today we probably wouldn't even be able to finish number 1. Because I'm going to have actually 2 bounds. One is better than the other. So here is a theorem for a Rademacher complexity bound. So the theorem is that, so suppose you have a hypothesis class that consists of models look like this, parameterized by theta, where you require that norm of W is less than BW, and norm of UI is bounded by BU. I guess I didn't define UI, so this is let me say this. So U is this matrix of M by D matrix, and let's say each of the rows is U1 transpose up to UM transpose, right? So so each UI is of dimension D, and so that's why U times X is really inner product of these UIs with X. That's the notation I'm going to use. Okay, so basically UIs are rows of the weight matrix. So we restricted the W and the norm of W and norm of UI to something like BW and BU. And then we also assume something about the data has expected 2 norm square less than C. I guess I should, this is probably C square. I have a typo here. So, and then under all of these assumptions, you can prove the Rademacher complexity bound Rn of H is less than 2 times BW, BU times C times square root M over square root N. So I guess just a remark is that this is not ideal bound, not a good bound, because M shows up in the bound. And actually it shows up in the wrong way because it says that if you have more neurons, you have a worse bound, right? So the M shows up in the more classical kind of sense, right? You have more neurons, you have more complex models, then it's not great, right? So, but this, so basically you cannot use this theorem to explain the size of deep learning or the over-parameterized model because this is saying over-parameterized model will have bigger Rademacher complexity, but you actually want something that you want a bound that is better when M goes to infinity in some sense, right? To explain the plot that I kind of like showed here, right? So you want that as M goes to infinity, you want a better and better bound in some sense. But this one gives you a worse and worse bound. But nevertheless, let's still prove this because this is kind of like a warm-up for what we will show next.
Why do we expect the bound to be better than M? Let's be like some really large we have both that idea.
I see. So maybe let me rephrase the question first, make sure. So you are, the question, if my understanding is correct, your question is that why you expect this right one is going to 0 or is decreasing forever, right? Instead of like really going up after a certain point, right? It's just we don't have enough data points, right? Like we didn't run that very super large scale experiment. I think the answer is that we do think this is already large enough for us to kind of believe that it will never go up. Like just because 4K neurons for this task is really, really a lot. Like 64 already allows you to memorize. Typically you wouldn't even run so many. You probably just, maybe it would be easier to convince you if I show you 4 up to 128. And you see something like this, and then you ask me the question, I will show you 128 up to 4K. You probably would be more convinced. But 4K is already pretty large, I think. That's, yeah. But of course, you can never rule out the possibility that after, maybe 1 million neurons, it goes up. It just sounds unlikely. Yeah.
I think you could, in the bound, the BW is the order square root M.
Mm-hmm.
And then that means the numerator is the order M.
Mm-hmm.
Then you could like combine the U say that substitute that for some norm of this thing.
Right. Right. So I guess I think the intention of the question was that whether this bound really is growing as m goes to infinity, right? So because BW could be, both BW and BU could depend on m. And maybe they depend on m in different ways. Maybe BW increase as m goes to infinity, and BU probably decrease as m goes to infinity. So that's definitely a possibility, right? So I think the thing here is that I'm choosing this scaling so that is at least arguably fun to think of BW and BU to be constant. So why? The reason is that this is probably a little bit vague. So the UI is the contribution of each component, right? So in some sense I'm choosing, but W is the contribution of all the components. So in some sense you are saying at the top layer you control the contribution from all the components, and you want to say that that's the constant. You don't want that to grow as m goes to infinity because so basically maybe one way to think about this is the following. So if you think about the scale here does make some sense, because UI is on the order of, let's say, a constant, then UI transpose at least a constant that doesn't depend on m, right? So UI doesn't depend on m, and UI transpose x doesn't depend on m. Here I'm writing this a little bit. I'm not. So here theta could probably have some dependency on d. We only care about dependency on m, let's say. So UI is on the order of constant, and then you have sum of wi phi of UI transpose x, right? So each of these terms is on the order of constant, and your wi, the total contribution, is constant. So that's why the total thing you can somewhat believe that this is on the order of constant, because it's not like each of the wi is on the order of constant. It's like the sum of the squares of them is on the order of constant. So in some sense you can believe that this whole thing is on the order of constant, especially if you have I guess it depends on how you think about this, right? So if you replace wi by 1 over square root m, then this is actually, let's see, so this is I guess depending on how you approximate this, like roughly speaking, if you use Cauchy-Schwarz, you're going to approximate by something like sum of wi squared a half times sum of phi of ui transpose x squared a half, and this is something. Let me see why this is on order of constant. Maybe we're actually even more generous than that. So the L2 norm of W is a constant, but I think you can still make this bigger if all of them are correlated, right? So if about this. Okay, so I think this is, I'm pretty sure the answer, I should have an answer, but I don't see I have a convincing answer right now. So maybe we can discuss offline for a few minutes. Yeah, but I think the scaling is chosen to be at least reasonably correct. Of course you can still argue certain, like there's always a, for example, depending on how W correlates with this, right? There's always some kind of like flexibility, but I think the scaling is relatively okay. Anyway, but it's a very good question, because you can have misleading results, if you are not very careful about the scaling. Okay, so let's see. Okay, so maybe I have 15 minutes. I think I can prove the theorem in the 15 minutes. So what we do is that we use the definition of the Rademacher complexity and gradually peel off the soup. So like we did before, right? We have a soup and we have to somehow get rid of it.
For your earlier argument, maybe you saw that they have the sum of WI times UI xi. The found that by just the sum of WI times the constant.
Right.
That's the one norm, and then you equal to norms to get a compare that to the two norm, which is differs by a constant.
Right. But differs by a square root m. So that's why I don't know. I was thinking to use your argument, but I think it's not going to be right because sum of WI phi of UI transpose X. I think the most pessimistic bound, right, would be something like this is less than, if you replace each of the WI by 1 over square root m, and each of these by a constant, you're going to have sum of this. And this will be square root m. So then, in some sense, this is not helping me to justify to use this scaling. So, right, but if you believe that there's some cancellation, so suppose you believe that there's a cancellation here, then this would be something on the order of 1. So basically, if you want to, so if you believe in there is a cancellation, then it's a reasonable scaling. Or in other words, suppose you want to make the scaling even smaller, right? Suppose you want to say that I'm going to believe BW is even smaller than the scaling I give, right? Or BU is even smaller, then you have to assume there's a strong correlation in your model. Otherwise, your model wouldn't even output something on the order of 1. So whether you are willing to do that. So for example, suppose I tell you that this actually experiences things, right? So then I have to convince you that I can choose BW to be on the order of maybe 1, and then UI to be on the order of 1 over square root m. And then this wouldn't go. The bound would not grow as m goes to infinity, but you will find that sum of BI phi of UI transpose X is very difficult to be big. You have to kind of match up everything to make it big enough to fit your label. So would you be willing to do that? I think you can arguably say that that's not really realistic. Okay, cool. So I guess let's prove this. So the proof, as I said, we're going to try to remove the soup in the definition of the Rademacher complexity, kind of like step by step. So first of all, let's define V to be the post-activation intermediate layer, right? Let's define phi to be U times X, which is an m-dimensional vector. And you can also correspondingly define Vi to be the corresponding activation for the ith example. This is in m dimension. And then using this notation, the Rademacher complexity on the empirical sample, the empirical Rademacher complexity is you take expectation, the randomness is from sigma, and you take soup. You have sum of sigma I transpose times, here you should write f theta of xi. But f theta of xi, I'm going to rewrite it as W transpose Vi, because just because that's the notation, right? So let me just replace this here. W transpose Vi, this is f theta of xi. And then here you take soup over two things, over both W and U is, the dependency on U is hidden in Vi. And let's clean up this to put the 1 over n in front, and you have soup over U and soup over W transpose times 1 over n times sum of sigma I Vi. I guess this probably looks familiar for you because we did something like this in the linear case as well. And then you can get rid of the W, but you still have the U. So you soup over U and you get rid of the W. W has L2 norm bound, so it's less than BW, right? So you get the soup of this is equals to BW times the L2 norm of sigma I vi. Right. Okay. So now we get rid of the BW. We can put BW in front. And now let's deal with the U. And the U is something like, wait, I think I shouldn't have one over in here anymore. My bad. So now this is a sum from 1 to n. And let's rewrite this. Let's plug in back the definition of vi, which is phi of uxi. And what I'm going to do is that I'm going to do a kind of like a, if you kind of get familiar with this, right, you can see that this is a very loose way to do this. I'm going to replace the 2 norm by infinite norm. So I'm going to say that this is less than square root m times the infinite norm of this. This is just because, any vector v2 norm is less than square root m times the infinite norm. And right, so if v is in m dimensional. Okay, so and now the reason why I want to replace it by infinite norm can be seen later, because because somehow with infinite norm I can simplify the soup. So now I have a soup, and note that what this vector is. This vector, maybe let's do something here. So this vector is a sum of a bunch of vectors, right? The infinite norm is about the dimension, the coordinates of this vector. So basically, each of this dimension is really something like sum of sigma I phi uj xi, and the sum is over I. This is the j's dimension of this vector. So basically, I can take soup over j and soup over u, and sum of sigma I phi uj transpose xi, and from 1 to. Right. And I can actually also write uj here, because if I take the soup over j, the j's entry only depends on uj. So, right, and that's actually kind of the main reason why we want to use this infinite norm, because once you write this, you found that all the j's are equivalent, right? So, like anyway, you're taking soup, right? So it doesn't matter whether it's uj or u1 or u2, right? So the soup is the same. So this is equals to. Is this the equality? Oh, sorry, this is an inequality. Yeah. So soup over u, a single vector u. So you replace uj by u, and you say that this needs to less than bu, because uj you used to have a bound bu, right? I just skip it for simplicity. So, and then you can write this as I phi of u transpose x I. In some sense, you remove the m dependency, because for infinity norm, how many m's doesn't matter. So, and now there is one step where I'm going to remove the absolute value, because if you don't have the absolute value, it's kind of like, let's first remove it. So by removing it, we'll pay a factor 2, and this requires something that is not exactly trivial, but I will not prove it in the interest of time. So you can remove this absolute value. And the reason, it's in the lecture notes. The reason is actually, fundamentally it's pretty simple. It's just basically because the soup is actually mostly positive, like almost always positive. Like because you can choose the u, it's always positive. So absolute value with or without absolute value, it doesn't really matter. At least for this case, right? Because you are taking the soup, right? So anyway, it's gonna be positive because you can choose u to make this quantity positive. Anyway, so this is what I like. This is I will ask you to refer to the lecture notes for the formal proof. And then now, after removing the absolute value, you can see that this is something like a Rademacher complexity of something simple, because this, you can view this as your function now. And this is the Rademacher complexity of this kind of function. But still you have phi and u, right? So that's why we are going to use the Lipschitz composition. So this will be less than 2, you copy all the constants. So this is by the Lipschitz. I think the Lipschitz composition or the Telegram lemma. So I think in some sense you think of like maybe you can define something like I guess maybe H prime to be the family of U transpose X. Right, and then you can also look at phi of H composed with H prime. So the Rademacher of phi composed with H prime is going to be equals to is this quantity, right? So and this is less than the Lipschitzness of phi, which is 1, right? And then you get H prime, which is this quantity. Okay, so that's the how we do it. And now it becomes linear. So U transpose Xi is a linear function class, and I think we have done this before. So for L2 norm constraint linear class, I think you can get something like this is less than 2 square root m bu over square root over n times, sorry, this is bw times bu times square root sum of xi to norm square. This is just by what we had for the linear model. Oh, sure. Yeah, sorry. My bad. Where the 2 come from? So the 2 come from here, this line. And this is the something I didn't explain, right? So like when you remove the absolute value. So can you get they are exactly the same without losing the 2? Is that the question? I suspect it's possible, but I'm not 100% sure. So like the proof in the lecture notes does lose 2, but it sounds like it's possible, right? You can save that factor 2. Because the intuition I had doesn't really tell you why you should lose anything, right? So my intuition is that this quantity is just always positive, so the absolute value doesn't matter, right? So that intuition didn't tell you why you should lose the 2. When I really prove the things, I think at least the proof I figure out, or I read from the book. Wait, maybe I figure out myself. I lose the 2, so maybe it's because I didn't do the right thing, exactly the right thing. Okay, so and then the very last step, you can take the expectation of the empirical Rademacher complexity. And this is the expectation over S, then you just get like what we did before, right? So the expectation of this is less than C times square root n, so you get this is bounded by 2 square root m bw eu times C over square root n. It's because you use a Cauchy-Schwarz for this part. This is exactly the same as what we have done for the linear models. Okay, so I guess this is a natural stopping point. And next time we're going to have a bound that somewhat improve on this so that you don't have the explicit dependency on M. Any questions? Okay, I guess I'll see you on Wednesday. Sounds good.